everyone. Today I will elaborate our research through 5 parts. Research background, research methods and steps, research results, research discussion, and research conclusion. First of all, let's face up to such a grim reality. With the remarkable changes in lifestyle and environment, the incidence of breast cancer has shown a steady and rising tide in recent years. Nowadays, breast cancer has become one of the main causes of cancer-related deaths in women, which undoubtedly sounded the alarm for us, making it an urgent and vital global public health problem. I'm Xiaofan, graduated from Southwestern University and now works in the Department of Pharmaceutical Affairs Management of the School of Medical and Health Management of Guizhou Medical University, engaged in risk management, placebo evaluation, and pharmaceutical affairs management. My position is Doctor, Associate Professor, and Master Tutor. I presided over and participated in 5 projects, with the first also publishing 6 SCI and SCI papers and periodical papers at all above the provincial level. Participating in publishing 2 core papers, participating in compiling a monograph, and independently compiling a monograph. In this study, we deeply analyzed the Wisconsin breast cancer data set and developed a powerful machine learning algorithm in order to accurately distinguish breast cancer from benign or malignant. Figure 1 is a diagram of our research process. We divided the study into 3 main steps and get the optimal algorithm. First of all, we aim to analyze the subset of features closely related to the benign and malignant features of breast cancer from Wisconsin breast cancer dataset. These features subsets are helpful to guide the medical field to explore the etiology, pathogenesis, disease development, and prognosis of breast cancer. Secondly, we try to train a machine learning model based on this future substance and evaluate its classification, occurrence, and generalization ability to optimize the occurrence diagnosis of cancer in benign and malignant breast. Finally, we evaluate the advantages and disadvantages of the breast machine learning algorithm trained on Wisconsin breast cancer dataset, which provides valuable insights and directions for algorithm optimization and deployment, and serves as a reference solution for solving medical problems by using machine learning technology. After pre-processing, analyzing, and visualizing the data, we developed and trained 6 different machine learning algorithms, essentially random gradient descent, random forest, KLN, SVM, logistic recurrency, and advanced logic. In this study, the final evaluation results show that the classification accuracy of advanced logistic model is as high as 99.21%, which effectively promotes the classification and the diagnosis of breast cancer. The following is our specific research process. The first is data collection. In this study, we use the Wisconsin breast cancer dataset obtained from Baidu Feijia Xiaofan study platform to build a machine learning model. This platform is the first in industry and deep learning platform with complete independent research and development functions and open source in China. The dataset consists of 569 rows of data distributed in 32 columns, of which 30 columns represent physiological characteristics related to breast cancer. One column represents ID number, and the last column represents breast cancer category. In our analysis, tumors are represented by B, and malignant tumors are presented by M. Secondly, we pre-processed the data and found 212 cases of positive tumors and malignant tumors in the diagnostic attributes representing breast cancer categories. After filling the blank data and coding the labels, in order to determine the appropriate statistical method, we used the normal test function in CSP library in patient environment to test whether the data conform to the normal distribution. After the normal test, we found that the feature data did not conform to the normal distribution as shown in Figure 2 and Figure 3. So we used the Spearman correlation coefficient to analyze the relationship between each attribute and the breast cancer diagnosis. Then we visualize the data by using the feature subset constructed by high correlation filtering of Spearman correlation coefficient. According to the correlation coefficients of 8 features such as pore parameter, pore radius, and pore surface positivity, etc. Table 1 shows the correlation and different Spearman correlation coefficients. In addition, figures 4 and 5 describe the Spearman correlations, and Tab 2 choose the Spearman correlation coefficients and the p-value of 8 feature 8. The following are 2D and 3D scatter plots created with these 8 selected data points as shown in Figure 6 to Figure 9. From the above picture, we can find that it is difficult to distinguish the linear differentiability only from the 2D scatter plots, while the 3D scatter plot reveals the linear separability pattern of the spatial distribution of benign and malignant breast cancer dates as shown in Figure 10 and Figure 11. These discoveries emphasize the effectiveness of using feature substance created by high correlation filtering in training classification algorithm. In order to determine the statistical relationship between data and features, we choose Wilson rank sum test after normality test. In these studies, we show the distribution histograms of 8 feature substance data and the future substance data distribution maps of different types of breast cancer as shown in Figure 12 and Figure 13. Table 3 also shows the parameter values and p-values of Wilson rank sum test on future substance data according to the parameter values and p-values of the future substance data. We find that the p-value indicating the feature itself is obviously less than 0.01, indicating that the distribution of two different feature substances is different, which is statistically significant. Subsequently, 80% of the dataset is allocated for algorithm training, while the remaining 20% is used to test algorithm performance. The training set consists of 284 cases marked as B in Table B and 171 is marked as malignant type M, where the test stand consists of 73 cases of type B and 41 cases of type M. In order to reduce the influence of different data contribution on the training speed of the model, inclusion 1 is used to standardize the training and test data. The box diagram of the standardization is shown in Figure 14 and Figure 15. After that, we use a variety of machine learning models to carry out simulation, training, and model comparison, and finally get the optimal algorithm. Figure 16 illustrates the training error and test error on decision tree algorithm and different max steps parameters. And Figure 17 shows the training and testing errors of a random forest model with different quantities of basic classifier in the machine-based forest model. When we use random gradient descent method, the cost friction is minimized by iteratively adjusting parameters, which leads to fast convergence and higher occurrence. When using KNN algorithm, it shows good performance when the spatial dimension of input variables is small and the actual class boundary is irregular. However, SVM algorithm shows strong performance in solving small, simple, nonlinear, and high dimensional classification and regression problems compared with decision tree algorithm, SGD algorithm, KNN algorithm, random forest algorithm, and SVM algorithm. Logistic algorithm has the best classification performance, so we use logistic algorithm as the base classifier to train the boost algorithm. Finally, the boost logistic algorithm with training set and test set fusion matrix are shown in Figure 18 and Figure 19, and its accuracy, precision, recurrent, and F1 value are shown in Table 4. The advanced logistic model achieves the best performance in the classification of B data with an accuracy of 0.99, a recurrence of 1.0, and an F1 score of 0.99. Similarly, the advanced logistic algorithm is tested on the classification of M dates with an occurrence of 1.00, a recurrent of 0.98, and an F1 score of 0.99, which also achieves excellent performance of M dates. It is worth noting that the average percentage recall and F1 value are reach 0.99, which is the best performance among the 7 machine learning models, according to Table 5 and Figure 20. According to Table 5 and Figure 20, these results highlight the superiority of the boost logistic regression model over the other 6 models in the risk constant dataset. According to the model training results, we summarized the training results in order to compare the performance of different models graphically. Table 5 shows the summary results, and Figure 20 shows the visualization of summary results. These results highlight the superiority of advanced logistic over the other 6 models in the risk constant dataset. On the contrary, compared with other 6 models, decision trees performance on breast cancer datasets is relatively weak. The area under cover is a commonly used index, which represents the area under ROC curve and can be used to predict the accuracy of a binary classification model. The AUC value ranges from 0 to 1, and the higher the value, the higher the accuracy of the model. Frequency recurrent cover visualizes the frequency and the recurrent of binary classification model and different thresholds. Figure 21 and 22 shows the PR curve and the POC curve on each node. The accuracy of advanced logistic regression model is 0.991228, which exceeds the accuracy of the other 6 models in the breast cancer dataset. Advanced logistic regression algorithm has the highest performance among the 7 models, showing excellent precision, recall F1 score, accuracy, training error, test error, and AUC index. In order to further evaluate its performance, we use the test data set to generate the forecast with the integrated advanced logistic regression model. Then these predictions are virtually displayed together with the actual values in 2D and 3D diagrams. Picture 23 and figure 24. The data visualization results show that the integrated logistic regression algorithm and advanced algorithm produce excellent performance on the test set. In addition, the model prediction is in good agreement with the test data set. With regard to data interpretability, we have studied 3 key aspects: the distribution of feature dates, the correlation between feature dates and the target dates, and the distribution difference between feature dates. We conclude that a high-quality feature subset data is helpful for the algorithm to learn the patterns in the data. In order to prove the excellent accuracy of our advanced logistic algorithm in breast cancer detection, we compared it with other complementary technologies. The subsequent results are shown in Table 6, and our advanced logistic regression method is superior to other methods in these aspects. In sum up, in this study, statistical methods were used to evaluate the normality of data in Wisconsin breast cancer dataset. Then the correlation coefficient between the target data and the future data is calculated by parameter correlation analysis. Then the future data with a high correlation with the targeted filtered to form a future subset. Finally, Wilkinson rank sum test is used to test the distribution of future subset data of various types of breast cancer using features. The accuracy of 7 machine learning models is predicted and trained, and the subset data is evaluated. The evaluation results show that advanced logistic algorithm has excellent performance in confirming and diagnosing breast cancer, and the accuracy rate is as high as 0.991228. This technology is expecting to play an important role in breast cancer screening and auxiliary diagnosis, greatly shortening the waiting time of patients and improving the efficiency of medical institutions. For the future research, we will continue to learn from the new clinical data on breast cancer. thus continuously improving the accuracy and generalization of the model. I hope our research can make greater contribution to the early diagnosis and the treatment of breast cancer and benefit more patients. Thank you.